And today I've got a nice experiment to show you. Perhaps not one you can repeat at home because you won't have the apparatus, but one I can show you in the laboratory anyway. Those of you who've studied a little bit of physics and perhaps done some electronics either at GCSE or A level will recognise these devices. These little electrical components are called capacitors, and their job is to store electrical charge, usually the size indicating how much charge they can store if they're capable of being connected to the same voltage. And most electrical circuits contain capacitors, and you can often see them in larger circuits. The circuit I'm showing you at the moment, the black circular things in the corner, they're the capacitors in the power supply. Now, what I'd like to do today is to see how we charge these up and how we can get the charge to flow off them. And I think the results will surprise you. I said a minute ago that this is an experiment you probably can't do at home. And some of you might be wondering why that is, because capacitors like this are freely available from electrical suppliers. And the reason is I don't want to show you the experiment today with these capacitors. What I'd like to do is to show it with something rather more unusual, and a capacitor from my collection, which is just a little bit bigger. This one here. And if you compare the sizes, I think you'll see that this is a 50 volt capacitor, so they're both a similar sort of voltage. This one has a much larger capacitance. It's very rare to find capacitors this large, in fact. But what we'll do is we'll charge up the larger capacitor and we'll see what it does when we release the charge. Okay, so what I'm going to do is I'm going to charge up this capacitor, and to do that I need to connect it to a power supply. I have to be very careful that I connect the positive of the capacitor to its positive and the positive of the power supply, so it's the right way round. So here we go, into the positive and into the negative, and the joy of these things is they charge very quickly. So let's disconnect it now and connect it across the light bulb and see what happens. And you might be slightly surprised if you've never seen these working before. So the lamp goes very bright and then dims very rapidly. I'll just repeat that so you can see it happening again, and give some thoughts to the amount of energy that's being stored in the capacitor. So it charges very rapidly, and then I'll disconnect it from the power supply, and what I'll do is I'll connect it across the lamp again, and you'll see the brightness of the lamp going dim very quickly. So give some thought to how much energy the capacitor's storing, and then you might think, well, it's not very much energy, but think about how it might compare to the little small ones I showed you. But we can take this a little bit further, and that's what I'm going to do next. So I'm going to do something slightly different this time. I'm going to charge up the capacitor again, so I'll just plug it into my power supplies and get it fully charged, and that takes a very short period of time. So that's the capacitor charged. Then I'm going to disconnect the leads from the top, and instead of connecting it across a lamp like we did before, which is quite a high resistance, I'm going to connect it straight across a single lead. And you'll notice you get a flash, you get a spark. It's such a good experiment that it's definitely worth repeating. So let's connect up across the capacitor. Charge it up, disconnect carefully, and then connect a very low resistance across its terminals. And there's quite a crack there. It usually catches me by surprise. So that leaves me to ask you one question. What happens if I charge this capacitor up, which I'll do now, make sure the power supplies are charging it fully, and then I ask my students this, I dare to put my fingers across both terminals. Well, you saw that great flash and spark. So what's going to happen? Is it going to fry me or what? Some of you should be thinking about resistance, so let's go for it. I always get a bit nervous doing this. Nothing happens. Should we just check? Whoa, quite a flash there. So it's really very strange. So what I want to do next is just very quickly explain to you what happened. So I'm rather hoping that what you saw then really surprised you. That I charged up the capacitor, I was quite happy to touch it with my fingers, and then I disconnected and I short-circuited it with a single cable, and there was an almighty flash. This is an experiment often set as a sort of scholarship type question thing, but let me give you a very quick explanation. When we charge up the capacitor, we're obviously putting electrical potential energy into it. And when we discharge it across a lamp, the lamp's got quite a high resistance, so the charge flows off fairly slowly. The current's quite low. When I use a single loop of wire and short circuit the capacitor, the resistance of the wire is very low, so the charge flows off very rapidly. Of course, what that means is there's a very high current and therefore a lot of energy per second, so quite a high power. You could use that in a welding situation. In fact, I've made the lead slightly black and slightly melted the metal. That was the flash you saw. But of course, when I connect my body across it, it wouldn't make any difference at all. The resistance of my body is so high that I don't flash, I don't light up. What of course happens is electricity will try to flow through me, but at very, very low current indeed. So I'm perfectly safe. In fact, I don't even feel anything. In fact, my resistance is so high that hardly any charge would have flowed through me at all. So when I take my hands off, the capacitor has remained pretty much fully charged. And that's why when I put the link back on, you get a big, large flash. So, always surprises me that. I do hope you enjoyed that experiment today and you enjoy your physics. I look forward to seeing you next time.